All right. So we're going to start by using the periodic blocks to write an electron configuration for chlorine in our 3 different formats. Okay? And then I'm going to have you work together to do the electron configurations of 2 different elements, and then we'll go over those. And then what we're going to do is we'll talk about D-block elements and trends in the periodic table. Okay. All right. Okay. All right. So remember that we can divide the periodic table into blocks. Okay, and those blocks will tell you, okay, what the highest L number orbital that gets, or the highest orbital shape that gets filled with any electrons in that element, okay? And so if you look at the periodic table, it's kind of these, sort of 2 towers with the flat area in the middle, okay? Our left tower is what we call the S block. The right, with the exception of helium, because it's very small, okay, is called the P block. Okay, and this in the middle, okay, is called the D block. So we're going to work with S and P blocks right now, and then we will talk about how to write electron configurations for D block elements, the actinides, and the lanthanides, those ones that are down at the bottom, those are what we call the F block elements, okay? All right. Okay, so if we were to look and try to do the electron configuration for chlorine, okay, we could look up its atomic number. What's the atomic number of chlorine? So we use the symbol Z for atomic number, if you remember. So what's the atomic number of chlorine? 17. What does that mean in terms of how many electrons we have? We have 17 electrons. Now we could try to paste all of the, or to write the complete electron configuration, okay? Or what we can do is we can use our blocks. So today we're going to use the blocks and to figure out, what those outermost electrons are, and then once you know that, everything lower than that in energy is already filled. Okay, so here's how we do it. All right, we find the position, okay, of chlorine on the periodic table. Okay, and so it is right here. What block is chlorine in? It's in the P block, right? So if I were looking, it's right here, okay? So it's a P block element, okay? We're going to use our period information, the rows, right? So this would be row 1, this is going to be row 2, this is going to be row 3. So it's in the 3rd row, okay, in the P block. Okay, so 3rd row, the P block, okay? Then what we're going to do is we are going to count from the beginning of where the P block starts. So this is where the P block starts, right? And so we'll count over. So 1, 2, 3, 4, 5. Okay. So this position tells us, okay, that that in chlorine, okay, we have electrons in the 3rd N level. Okay, so we're going to be going up to here, okay? And that there are 5 electrons in that 3rd N level P orbital, okay? So let's start there, okay? And we're going to follow all of our rules, okay? And we're going to put one electron at a time in each orbital. So that's 1, 2, 3, 4, 5. Okay. Now, so that's kind of our outermost orbital. And then we know that everything below that has got to be filled before those fill. So we can just draw in all of our little electron arrows, knowing that that is filled. Okay. We're going to double check, okay, by counting up the electrons that we have, and we should have 17 electrons, right? So we've got 2, 4, 6, 8, 10, 12, 14, 16, 17. Okay? So we've got our 17 electrons placed. Okay? So that would be how to do the orbital box notation for this. Okay? If we were going to take this and then turn it into a SPDF notation, okay, what we would do, okay, so I'll put that in purple. Okay. So this SPDF notation. So this is orbital box. All right, so orbital box, we're going to say each type of orbital, how many electrons there are. Okay, so we got 1s2, 2s2, 2p has 6 electrons there. Our 3s has 2, and then our 3p has 5. Okay. So both of these types of representations give us all the, the information about where all the electrons are. Okay? But, as we progress toward how materials actually behave and their chemical reactivity, okay, as we progress towards knowing what the periodic trends are, the electrons that matter the most, okay, are going to be what we call our valence electrons. Okay? And so we'll talk about what those valence electrons are in a minute, but the notation that helps us see just our valence electrons the best, okay, is our noble gas notation. So let's do the noble gas notation now, okay? And so we'll put that in blue, okay? All right, so if we remember our noble gas notation, okay, we're going to look at the noble gas, the row above, okay, so that would be, if we look the noble gas at the row above, is going to be neon, okay. So we would write neon, in square brackets, and we're only going to write electrons over and above neon, okay? So neon is in the second row of the periodic table, okay? When we look at, the electrons that chlorine has over and above anything at the n equals 2 level, okay? Well, our p block, right, positioning tells us that we have 5 electrons in the third p orbital level, okay? And we know that s has to fill before that, okay? So we would have 3s2, 3p5, okay? Neon, again, has 10 electrons. Yeah?
How is neon closer to it than argon?
Because it has less electrons than argon. So we can't say it has the core electron configuration of argon, because argon has more electrons than it. So it's like when when you're playing a guessing game with numbers, and it's like, okay, who can get closest without going over? So when we write this, we're saying it's got 10 electrons placed in all those orbitals that would get us up to 10 electrons, okay? So yeah, even though argon's right next to it, argon has more electrons. So it's the nearest noble gas that has less electrons. Yeah, yep, without going over. All right, so let's look at a few things, okay? So, neon has 10, and when we use noble gas notation, oh, yeah.
How come we just put those two numbers after the neon?
So, because when we write neon in square brackets, what we're writing is this. Chemists understand it to mean that. It's a shorthand for that, okay? So we're only writing those kind of over and above that core, okay? And the reason that that's important to us, okay, so neon has 10 electrons, so this is our 10 inner electrons of chlorine, okay? And then these are the 7 extra electrons, or the 7 electrons that chlorine has that neon doesn't. And we call these the valence electrons, okay? So our definition of valence electrons, okay, is going to be, okay, the number of electrons in the highest n level, okay? Or when we get to the D block elements, we're going to see we will count electrons in a 3D orbital. If we have electrons in a 4s, because it fills before the 3D, we're going to count 3D orbitals and the 4s if the 3D is not completely filled. So we'll get there. But for now, okay, our valence electrons are going to be those that are in the highest n number, but with the noble gas notation, our valence electrons are the only ones we show explicitly. The rest we use the shorthand for, okay? So that's thing number 1. Thing number 2, look at your periodic table. Look at chlorine. What is the group number of chlorine in the AB notation? Yeah. It's 7A, okay? That number, 7, tells us how many valence electrons we have. Okay, so for the S and P block elements, okay, you can double check yourself when you're trying to figure out valence electrons by just looking at what that group number is. Or, again, shorthand from the periodic table is that column number tells you the number of valence electrons, okay? So that's for the A groups. When we get to the D block, we'll talk about the B groups, okay? All right. All right, so we have our 3 different notations, right? And they all say the same thing. They all give us the same information. It's just the different representations condense it and put it into more shorthand, okay? All right, so again, it is going to turn out, okay, that our valence electrons are going to be the ones that are responsible for the chemical properties of the element, okay? Or the most responsible. We can predict behavior based on how many valence electrons there are. All right? All right, so what we're going to do now, okay, is I want you to work in your groups, and you're going to do magnesium and calcium, okay? Whoops. So, there we go. So you're going to write all 3 representations for there we go. For magnesium and calcium. Okay? And then we'll go over them, we'll talk about valence electrons, and then we'll move on to the D block. Okay? All right, so collaborate with your neighbors, and I will come and pass these around. So while the handout does have this, orbital filling diagram on it, try using the block and counting where you are, okay, to figure out. All right, putting this back up, okay? All right, you guys need your periodic tables out. Well, that's your team. So you're gonna find it. All right, I'll block it. Third row, this is okay, so are going to use like, so first of all, what's your element? You always have to have one out. Well, so when you're filling partially, like when you're filling pure, you put one electron in each first, and then you pair. Okay, so you have the P, when you're filling it has two electrons, so one has to be an L2. We're gonna get C. Okay, so now, which number is that? Is that what you got? Because I just added. It's gonna be faster. I was thinking those numbers, I was like, that's necessary, and I was like, well, that's easy. Yes, I just added. So we're using that's and then you're just going to write the highest n number of electrons. Yeah. Neon and square bracket. We're looking at magnesium. Now we're ready to make so So we've done this. No. Okay, so when you write me out this photograph, what you're writing is okay? It's shorthand brown. Okay, so if we want to write our two iterations where I think we're all we ever see. And we're going to go over this as we go over. So you're going to use the position, okay? And put in the your S block. Okay, so figure out what's your skills, how many you have in it, and then everything below that is going to be. Alrighty, folks. So let's go over these two. Before I start writing on this one, I'm going to duplicate the slide so that we can do. Let's see, duplicate. Thank you. All right, so we're going to do magnesium, and this one's going to be calcium. Okay. All right. So magnesium. What we're going to start with is identifying its location on the periodic table. Is it in a D block? Is it in an S block? Which period or row is it in? Okay. So when we look at magnesium, okay, it's here. It's an alkali metal. Okay, so which block is it in? Is it S, P, or D? It's in an S. Yep, it's in the S blocks. So this is our S block. Okay. All right. So that tells us that our highest energy orbital is going to be an S orbital. Okay. And what number S orbital is it going to be? Is it going to be 1, 2, 3, 4, 5, 6? We're going to look at the row number, right, to figure out whether it's what its N number is. Okay, so the row number tells us 3, okay? So we know, okay, we're going to be, our highest energy level is going to be this one, the 3s. Okay. Is everybody with me so far? Okay. All right, and so now we just have to figure out, well, how many electrons does that 3s orbital have in it? Okay, s orbitals can have up to 2 electrons in them, okay? And when we're using our p block, s block, kind of shorthand, we're going to count over how many blocks we are in from the left of the beginning of that block, okay? So the block begins here, okay? So sodium is the first one and magnesium is the second one, okay? So that means that there are 2 electrons in the 3s orbital, because we are the second block in the third row of the s block, okay? So we'll put those electrons in. They have to have opposite spins, so one goes up and one goes down. All right, so now that positioning on the periodic table tells us about the outermost electrons, okay? And remember that electrons are going to be filling in all lower level energy levels before they get to that outermost level. So we know that all of these other ones are going to be completely filled, and so we can just draw in our little arrows without even thinking. Okay. All right, so now we're just going to do a check, okay, and make sure that this is consistent with our atomic number. So what is the atomic number of magnesium? Remember, this is our atomic number. So if we go on the periodic table, it is, I heard somebody say it loud, say it proud. 12, okay? So those little arrows have to add up to 12. So if we do that, we've got 2, 4, 6, 8, 10, 11, 12. So we've placed 12 electrons, we're good to go, okay? All right, so that's noble gas. That's our orbital box. So now let's do our SPDF, and that is going to list each orbital type and how many total electrons is in that type, okay? So we go we have got 2 in the 1s orbital, so we go 1s with a superscript of 2. Then we've got our 2s orbitals, that has 2. Our 2p has a total of 6 electrons, okay? So we would write 2p6. So this is where the SPDF notation is a little bit of a shorthand over the orbital box, because it treats all 3 of those p orbitals as just kind of one thing, okay? And then we've got 2 electrons in our 3s orbital. Okay, so that is our electron configuration in the SPDF notation. Okay. And now we want to do the noble gas notation. Okay, so the thing that we have to do is we have to look at our group 8A, which is our noble gases. We have to look at the row above. We have to look at the noble gas that has less electrons than the atom that we're considering. So that would be, once again, neon, okay? And so for the noble gas notation, okay, so this right here, we're going to start with neon in square brackets, okay? Now this is where the noble gas notation becomes shorthand, because when we write neon in square brackets, what we mean is this. Okay, neon has 10 electrons. If we wrote the electron configuration out for that, it would be this right here, 1s2, 2s2, 2p6. Okay, so the noble gas notation saves us a lot of writing, okay, as we get to larger and larger elements. But that's not really like why we like to use it. The reason we like to use it is because it only shows us the valence electrons explicitly. Okay, so we would write, the noble gases, and then we're going to write the outermost electrons. Okay, so that is going to be anything that is above level 2, because this was in row 2, right? And so what we're going to do is we're going to write the electrons that are in level 3, and so it would be 3s2. So that's our noble gas notation for magnesium. Okay. All right, so now let's move on to calcium. Where is calcium positioned? So it's not shown here. So if I were going to write calcium on this kind of bottom corner here, where would I write it? Which element would I write it below? What's that? Magnesium, yeah. So calcium, whoops. Calcium's going to go right here, okay? All right, so let's start with our blocks. Which block is it in? S block, thank you. All right, so it's an S block element. What period is it in? So it's directly below magnesium. So it's in row 4. And how many blocks in is it? Okay, if we're going from the left? 2. Right. So it's the second from the left. So that tells me that my outermost electrons are 4s, right? So I'm going to have to draw in an extra box here. Okay. It was an oversight on my part. All right, so I'm going to have electrons, okay, in that 4s orbital. There's going to be 2 of them, right? 2 electrons in the 4s orbital. Okay, that's what the position tells me. And everything below that is going to be filled. All right, so if we do SPDF notation, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So you can see, even just going one row down, these things start to get longer and longer. All right, what check did I forget to do? I forgot to check against the atomic number and make sure I'd place the correct number of electrons, right? All right, so let's see. What is our atomic number of calcium? Calcium is 20, so we should have 20 electrons. So we've got 4 here, 6 there, that's 10. And then we've got another 8 there, that's 18. And then 2 more, that's 20. Okay, so we've got 20 electrons. We did it right, okay, or at least we're consistent. All right, last but not least, our noble gas notation. So which noble gas are we going to use to represent this core? Everything up to the highest number electrons. We're going to use argon because it is 1 row above, so it's the nearest noble gas that has less electrons than our element. So we're going to write that as argon, and then the only electrons that we need to show, are our 4s2 electrons, okay? All right. Okay, so again, one of the reasons that I chose calcium in addition to magnesium, it may seem like it's boring because it's just kind of the same thing. It's in the same column of the periodic table, but that's the point. Okay, what column are we in the periodic table? If you look at it, it's not going to be listed up there. I'm talking about the AB notation here. So if we look at the top of the column that calcium, magnesium are in, what is it? It's 2A, right? So these are in group 2A, okay? And what was common? What is common to both of these elements? How many valence electrons do they have? 2, okay? So if we were to move around the periodic table in the S and P blocks, what we would find, okay, is that everybody in the same column has the same number of valence electrons, okay? They're only going to differ in what that n number is before the highest energy orbital. So let's just quick, okay? We're going to pick barium, okay? So let's pick barium, okay? So let's write barium in the noble gas notation. We're not going to count, things. We're just going to look at row number, column number, and the noble gases. So which noble gas are we going to pick? Xenon, because that's the one that's above it. Okay. And we know there's going to be 2 valence electrons because it's in group 2. Okay. And what's the n number for that? So what row is it in? 6. 6s2. Look at that. We did that in like 10 seconds. Okay? Yeah, Ben?
Out of curiosity, what if we do something like beryllium? Would we use helium?
Yes, you would use helium.
Use helium?
Yep. And then helium and hydrogen is, it's got 1 electron. So, there is, it doesn't get any shorter than 1s1. So, yep. All right. Okay, so remember how we kind of started this with talking about like what makes materials magnetic or whatever? So remember that if we have something that is diamagnetic, okay, we're going to have all electrons are going to be paired, okay? And then if we have something that is paramagnetic, okay, we're going to have at least, oops, how about if I start actually writing things correctly? All right, we're going to have at least 1 unpaired electron. And paramagnetic elements can become magnetic if all of those spins are lined up, okay? So let's classify these elements as if they, as according to whether they are diamagnetic or paramagnetic. Okay, so looking at their electron configurations, okay, we've got our friend beryllium here. Okay, so is beryllium diamagnetic or paramagnetic? Diamagnetic. Okay. All right, how about carbon? It's paramagnetic. Yep. How about fluorine? It's paramagnetic. And how about neon? Diamagnetic. Yep. And again, we would expect all of the noble gases to kind of behave that way, right? Because they all have 8 electrons in their outermost shell. All right. So now let's talk about the D block, okay? Because the D block is, has more electrons. And when we get to D, okay, and we're looking at orbital energies, okay, you'll notice that 4s is going to fill before 3d, okay? So we're going to have to use a slightly different process for this, okay? So we're still going to figure out our position on the periodic table, okay? And we're going to figure out how many total electrons we have, okay? But we're going to have to fill that 4s orbital first, okay? All right, so let's look at an example here. So we're going to look at iron. All right, so iron is our test case, okay? So if we look at iron, here it is on the periodic table, okay? And this element, all right, so this is where our D block begins. Okay. and this is where the D block ends, okay? So just for a second, let's rewind and think about our D orbitals, okay? Remember that we've got, at every n level, we have one S-shaped orbital that can have 2 electrons, right? When we have p orbitals, okay, there are 3 separate shapes, okay, that they can be in, each of which can have 2 electrons. So at any given n level, we can have up to 6 p electrons. Does anybody remember how many D shapes are there? So number of D orbitals. So you've got 1 for S, 3 for P. Yeah. 5. Excellent. Yeah, we like our little prime numbers there, okay? So there are 5 of those. So D orbitals can hold up to 10 electrons, okay? At any given n level, okay? All right. So let's just count, shall we? How many elements, okay, are in the D block as you go across. So if we start with scandium, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretty cool, right? So now, remembering, okay, that our 4s, okay, so this is row 1, 2, 3, 4, is going to fill before the D, okay? What we're going to do when we write the electron configurations, okay, is we are going to count where we are in the D block, okay, and we're going to put that number of electrons in the D orbital, but we have to remember that we have to fill the S or the S orbital first for that row, okay? So let's do it for iron, okay? So if we do it for iron, okay, iron is, 1, 2, 3, 4, 5. It's 6 blocks over, okay? So it's 6 blocks in from the beginning of the D block. Okay. And we are in row 4, okay, so we're in period 4, okay, so in period number 4. Okay, so we know that we're going to go up to this n equals 4 what would you call it? Subshell, all right? And so we're going to fill our, and the d orbitals, okay, that the n level we're going to fill, okay, is going to be 1 number less than your row. Okay, so that's the kind of, so our s orbitals are going to be 4s, but our d orbitals are going to be 3d. Okay, so that's the one trick when you're doing d block things. Okay, the n number is going to be 1 less than the row that they're in. Okay, all right. So let's do this. Okay, so this is going to be in period 4. So we're going to be filling 3d orbitals. Okay, and we're going to put 6 electrons in them. So I'm going to zoom in because I can. Okay, so we're going to do 1, 2, 3, 4, 5, 6. And remember, I do individually before I start pairing. Okay, and everything below that is going to be filled. So all those go. All right, so we're going to do our check, okay? What is our atomic number for iron? It's 26, right? So, sorry. So, C for iron is 26. So let's count up and see if we've added 26 electrons. So we've got 4 and 6 is 10, 12 plus 6 is 18, 20, and we have placed 6 here, okay? So we have placed the correct number of electrons, okay? All right, so now the last kind of wacky trick about things that are in the D block, okay, is we consider, okay, we consider the d orbitals and the highest n number s orbital are valence electrons. Okay, so if we were looking at who our valence electrons are, okay, we're going to call our valence electrons both of those guys. Okay, so we have, so what we would do, okay, is we're going to go one row up. And argon is our noble gas that's closest without going over in atomic number. Okay, so our noble gas notation is going to be argon. And then we're going to have the 4s. We have 2 there. And then our 3d, we have 1, 2, 3, 4, 5, 6 electrons in there. Okay. So if I want to consider how many valence electrons iron has, okay, then we would say we would add up those electrons. Okay, so this would be 8 valence electrons. All right, look at the periodic table and look at the column numbers for B. Okay, or the B column numbers. Which column does iron fall in? It's 8B, right? Okay. Now you'll notice that there are 3 columns that are considered 8. Okay. This is the transition metal behavior gets a little less predictable. This is where we're going to find our exceptions to some of the rules. So we're going to, when we're asking you to do electron configurations, we're going to do the predictable ones, okay? But again, we can do a double check on whether we did things correctly by looking at those top numbers. And so just for the purposes of being complete, we would do our SPDF notation by, again, including every single orbital and the number of electrons that are in it. And we usually write them in the order of energy going from low to high. And so that's iron, okay? All right, so try to do, go home, try to do the electron configuration for zinc, and we'll start with that on Wednesday. And then what we're going to do is we're going to take this information and we're going to use it to explain behavior of atoms, like their size and how easy it is to take electrons away from them or give them electrons. Okay? All righty. Have a good one. This week's